Hello, everyone. In this video and in the subsequent videos, I want to talk about regression. So regression belongs to supervised learning. So supervised learning is a class of learning techniques in which we seek to learn the relationship between some input here denoted as X to some output. So here X is the input of our data and Y is the output. We seek to learn this relationship from some measurements on X and Y. We have pairs of measurements and we seek to learn this relationship. So algorithms of this type belong to supervised learning. Regression is a particular kind of supervised learning algorithm, which Y is continuous. So in a regression model, the output is actually continuous. So let me give you an example. Let's say X is time and Y is the temperature Pittsburgh for that particular time. So we know temperature Pittsburgh adds a continuous number. It can get any real value, although within a range, but can't still get any real value. So in that sense, the output is continuous. On the other hand, we have this other class of problems called classification, supervised learning techniques called classification, where Y is discrete. So an example of a classification problem is where X is the pixels of the image of a digit, of a single digit, and Y tells us what that digit is. So Y is either 0 or 1 or 2 or all the way to 9. So Y can only take any of these 10 values, and so it's a discrete value, and in that so that is a classification problem. But I want to focus on regression in this video and the next few videos. And through regression problems, we want to learn some of these basic machine learning terminologies as well as some core concepts in machine learning. So let me give you an engineering problem, an engineering example of regression model and how we use a regression model. So imagine we have a tank of a liquid, some liquid. And so within this tank, we have a body that is fully immersed. Let's say this body has the same density as the liquid, so it's buoyant, so it can travel freely here. Once in a while, in a random fashion, it comes to the surface. And when it comes to the surface, we have some infrared camera, which we can use to get a measurement of the temperature of this body at that particular time that it appears at the surface. And so we can collect this data in the form of a table where here X is time and Y is temperature. And so whenever this body comes to the surface, this X1 would be the first time it appears at the surface, and Y1 with temperature at that particular time. So we collect this data and let's say we made n observations. And obviously this camera cannot be perfect, so it makes a noisy measurement of temperature. It's not exact temperature, it's just noisy measurement. So we should assume that there is some noise in this data. It's not perfect. Okay, so we should take that into account. And let's say I plot this data. This is scattered data points that we collected. And then one may want to know what the temperature is at some other point for which we don't have any measurement. For example, take this time. So let's say I want to know what temperature is at this particular time, which we can call it X star. I don't have any measurement here. And so basically I want to use the measured data to make some prediction at this new point. And so one of the utility of a regression model is doing just that. So basically we can learn this relationship between Y and X. Once we learn that relationship, then we can use our learned model and evaluate it at the new X. So assume that what we learn looks like this. So we can learn that from these labeled data here, and then we can make a prediction here. Temperature here is this value. Okay, so in that sense, this regression model serves as a surrogate model. Once it's learned, we can use it for new predictions. So let me talk about a particular kind of regression model. I want to talk about specific kind of regression model. So let's put that in more mathematical terms. So why the measurement is a function of x, and that's the relationship we are trying to learn. So we have to choose a model. And I'm denoting that model as f of x and then semicolon theta, and we'll explain these terms here. And then this model is a continuous model, so we add eta, which denotes the noise here. So this is a parametric regression model. This is a parametric model. Eta is the measurement noise. And theta, it's the vector of model parameters. It's not just one value, it's a vector of all the parameters, which is actually the thing that we are trying to learn here. So this is a generic form of parametric model. So I want to emphasize this is a parametric model. We also have non-parametric models, but I'm not going to talk about that. So we're going to focus on a particular class of regression techniques where the model is parameterized by this vector theta. And one can look at this data and then choose a polynomial model for regression. If I choose a polynomial model, let's say a polynomial of degree 3 seems appropriate here. Then I'll introduce 4 parameters, obviously. So in this notation, theta is the vector of unknown, the model parameter, which now contains four parameters. And so the objective of regression model training is to use this data, this labeled data that we have, and learn these 4 parameters. And so I want to make another point about this particular model that I've chosen. This is a linear regression model. And this might sound confusing because when we think about linear regression model, we would think that, oh, we need to just keep these 2 terms. That would be a linear regression model. But adding these terms make this nonlinear. That's true in a sense. This is a nonlinear model in terms of the x. But when we call a model linear model, we look at the dependence of f to theta, not f to x. Okay, so we distinguish that. So f with respect to theta has a linear relationship. Right? So theta just shows up with exponent 1 here in all of these things. So that's a linear model. Although the dependence of f to x is nonlinear, so if we look at the choice of the model we've made here, we chose a polynomial model, and so we have 1x, x squared, x cubed. These are called feature space, and in the feature space, this is nonlinear, but that doesn't make this regression model nonlinear regression model. It is a linear regression model. And you will see because the dependence of f to theta is linear, that allows us to use some simple algorithm to find theta. Basically, we will solve a linear system to find theta. An example of nonlinear regression models are neural networks. A very, very simple example. If we had chosen a model of this form, then the dependence, and I have to make the dependence of f2 theta. Place it f of x and theta. Dependence of f to theta here is nonlinear. And we will see that we have to employ different kinds of tools to find theta here from that data. But here, it's much easier. So this is the nonlinear model. And initially, we're just going to focus on linear model.